Now that you know how to use separation of variables, now we're going to take it to the next step where we actually find particular solutions as opposed to the just plus c. So if you remember from before when we did some differential equations and solving for particular solutions, the very first thing we had to do was find the general equation, because then I could plug in my x and my y information in order to find the particular solution. So doing that on the first example, I'm going to go ahead and try to get all of my x variables on one side and all of my y variables on one side. So doing that, first thing I'm going to do is I am going to subtract this xy dx from both sides. Doing that, I will have e to the negative x squared times y squared minus y dy equals negative x y dx. And then from there, I'm going to go ahead and divide by e to the negative x squared and also divide by y. So I will have then left over here y squared minus 1 all over y dy equals negative x dx over e to the negative x squared. I'm going to go ahead and put this as y squared over y and 1 over y because I know I'm not going to be able to integrate as long as there's a quotient there. So doing that, that's going to give me y squared over y, which is y, minus 1 over y dy equals, also I'm going to go ahead and move this e to the negative x squared up, because then when I do, the exponent will lose its negative, it'll lose its ticket, and it'll become positive. So then I will have negative x e to the positive x squared dx, and now I'm ready to go ahead and integrate each side. So I'm going to go ahead and squeeze my integral signs in. And then integrating this, I see y is going to become 1/2 y squared minus 1 over y, which is going to be minus ln absolute value of y, equals, over here, I'm going to have to use u substitution. So I'm going to go ahead and let u equal x squared, and then du dx equals 2x, and du is just 2x dx. So I have the x, I have the dx, I'm going to pull the minus out to the front, and to get a 2 in there, I'm going to have to put a 1/2 out front. So before I integrate, I'm going to rewrite it, the integral as the integral of 1/2 times the integral of e to the u du. So then my new equation will become 1/2 y squared. I'm going to anticipate that this is going to give me e to the u back and be exponential, so I'm going to drop my exponent, or my absolute value bars, ln of y equals negative 1/2 e to the u was x squared, and then plus c. So from here, typically what I would do is I would solve this for y to try to get y by itself. The issue that I'm seeing with doing that is that there are two separate y's here. I can't factor them out, because this belongs to the ln. So I'm going to actually skip trying to rewrite this in a form that has y by itself, and I'm going to go ahead right away and find my particular solution. So when I find my particular solution, I am going to use the fact that when x equals 0, y equals 1. So I'm going to plug in 0 for x and 1 for y, and I'll have 1/2 times 1 squared, which is just 1/2, minus ln of 1. Remember, ln of 1 is going to drop out and be 0. The reason being, so just a little scratch work over here, if I have ln of 1 equaling something, if I change that to exponential form, e to the what equals 1? Well, the 0. So this is just 0. But taking care of that, my next step, and then finishing this, equals negative 1/2 e, x was 0, so 0 squared is 0, plus c. That gives me, as I had said before, this is going to drop out and become 0. E to the 0, of course, is going to be 1, so I will have 1/2 equals negative 1/2 plus c. Solving for c, then I get c equals 1. So my equation becomes, using this original equation here, 1/2 y squared minus ln of y equals negative 1/2, I'm going to run out of room, ex squared plus 1. Got it. And that would be the particular solution to my equation. Again, I am unable on that one to get y by itself, but that's okay. Moving on from here, looking at my second example, again, I'm going to find an equation of the curve that passes through the point 1, 3 and has a slope of y over x2e at the point xy. Note that I'm told that y is always positive on this curve. So if I'm trying to find the equation of the curve and I'm given the slope, in essence, I'm given the derivative. So if I'm given the derivative, then I'm going to go ahead and use that information to solve that differential equation and find the particular solution. So if slope is this, that means that dy dx is y over x to the 2e. And looking at my notes, that e is not supposed to be there. Because I'm worried that it'll turn out funky if I don't get rid of it, I'm going to go ahead and do that, and I'm going to fix this just to be y over x squared. Okay, and now going ahead and solving, I am going to go ahead and multiply both sides by dx because I do not want to have my dx in the denominator. Same thing, I never want my dy in the denominator. And then I'll work from there. So I'll have dy equals y over x squared dx. And now from here I can leave it as 1 over x squared. I'm also going to multiply both sides by 1 over y. And I will have 1 over y dy equals 1 over x squared dx. And now I'm ready to integrate. So sticking in my integral, I see that 1 over y is right away going to become ln absolute value of y equals, and so I have 1 over x squared. So before I integrate this side, I'm actually going to bring the x squared to the top and make it x to the negative 2. Giving me, once again, ln absolute value of y, but because I was told that y is always positive, I can go ahead and just make that ln of y equals negative 1 x to the negative 1 plus c. If I go ahead and solve this for y to get my general solution, first I will have e to the negative x, negative 1 plus c equals y. So remember, I can split that up and say y equals e to the c times e to the, I'm going to go ahead and say negative 1 over x, because remember that is the same thing as x to the negative 1. It really does not matter which way you write it. So then that gives me my general solution, and of course my plus c of y equals e to the c, remember, is just some constant. Call it c. E to the negative 1 over x, and I'm sorry I was not supposed to write this plus c here because I took care of my plus c when I brought it up, so that was where my plus c went. So here would be then my general solution, so I want to find the particular solution. So to do that, I'm going to go ahead and notice that it goes through the point 1, 3, so I get 3 equals c, e to the negative 1/3. So oftentimes I want to leave it exact, so I'm going to go ahead and say c is then 3 over e to the negative 1/3, which is the same thing as saying c equals 3 e to the positive 1/3 if I bring it up and let it lose its ticket. So then from here, I'm going to go ahead and actually, before I go any further, I see that I plugged 3 in for both x and y. Or excuse me, yes, so I was supposed to put x equals 1 in, so this actually should have been a 1. So giving me c equals 3e to the 1, which is just 3e. So now writing out my general solution, or excuse me, my particular solution, I'm going to go ahead and use the equation that I got right here for my particular solution, but in place of c, I am going to plug in 3e. Giving me y equals 3e times e to the negative 1 over x. Remember that same bases being multiplied, I can put them together as one base. So I would probably rewrite my answer as y equals 3. So e 1 plus negative 1 over x ends up being 1 minus 1 over x, and that would be my particular solution for this equation. Looking at the next example. Again, I'm finding a particular solution. Again, I'm given a differential equation and an initial condition. So I'm going to go ahead and set that up as dp over dt equals 2p minus 2pt. So I'm going to go ahead and anticipate that I'm going to have to get p's on one side and t's on the other, and I'm going to factor out a 2p, leaving me with 1 minus t. And now I'm going to go ahead and divide by 2p and multiply by dp, giving me 1 over 2p dp equals 1 minus t dt. I'm going to go ahead and squeak an integral in. You can see that. So then the next thing I'm going to do is I'm going to go ahead and see that I have this constant of 1/2 that I can pull out to the front, giving me 1/2 times the integral of 1 over p dp equals the integral of 1 minus t dt, which gives me 1/2 ln absolute value of p equals t minus 1/2 t squared. So now from here, I'm going to go ahead and I'm going to solve for p. So first thing I'm going to do is I'm going to get rid of this 1/2. So I'm going to multiply everything over here by 2, giving me ln absolute value of p equals 2t minus, when I multiply 1/2 by 2, of course it just drops away, giving me t squared. And then raising it, changing it to exponential form, I get e to the 2t, and I did forget my plus c here. Sorry about that. Minus t squared plus c equals p, lose my absolute value because it is exponential. So now from here, I've looked before about separating. I am going to separate, and I am going to make this e, and I'm going to leave these 2t minus t squared times e to the c, so that then I can make e to the c become a constant. So doing that, I get e to the c times e to the 2t minus t squared equals p. So some kind of constant times e to the 2t minus t squared equals p. There would be my general solution. If I want to go ahead and find my particular solution, I'm going to go ahead and say that when t is 0, p is 5, pulling that from up here in my conditions. Then that gives me c e to the 2 times 0 minus 0 squared, so e to the 0 equals 5. So c times 1, so c equals 5. So I get 5e to the 2t minus t squared equals p for my final answer. So one thing I want to point out is that notice that in this problem, this is what I got for my general solution. I got this c times e raised to something. If you look back at the previous example, I also got c times e raised to something, which brings me to my last point. We're going to see this all the time. If we have a differential equation that tells us dy dx equals ky, so we know that our y is proportional to the rate at which y is changing with, say, for example, x or t or whatever variable I'm given, then we can follow this formula. I tend to not use the formula. I tend to just use separation of variables, but I do want to show you how it works if anyone chooses to use it. If I had noticed here that, so p is essentially my y here, so I have the rate at which p is changing with respect to time. If I had noticed that if I pulled just a p out, I had 2 minus 2t left, then notice that k, the thing that my variable, my y variable, in this case my p variable, is being multiplied by, is 2 minus 2t. That would be my k. If I knew the formula, I could say then that y, or in this case p, equals some c times e to the k, which is 2 minus 2t. So it does not give me my particular solution. It does give me my, times t, sorry, I forgot it's k times x, I forgot, so times x, which in this case is t, so I would get p equals c e to the 2t minus 2t squared, so it does indeed match what we got. So notice it doesn't give me my particular solution. All it does is give me, my general solution. So I would still have to go back and solve for the particular solution, but it is a shortcut if you see that it is in this form. Not every single differential equation is going to be able to be put into that form or will be given in that form, but if it is, then you can use the formula to take a shortcut.